Welcome to Power Electronics lecture series. In this lecture, we are going to discuss about third unit in the Power Electronics subject, that is DC to DC converters. Those are nothing but choppers. Coming to major concepts in the third unit are: first one is the introduction and applications of choppers. Second one is types of choppers. Third one is the power circuit analysis and waveforms of different types of choppers. Fourth one is types of chopper circuits, and the fifth one is voltage control strategies of choppers. All these concepts are very simple. Now we are going to discuss each and every concept in detail. Coming to introduction of choppers. Here chopper circuits are also known as the DC to DC converters, and chopper is defined as it is a circuit which converts the fixed DC voltage to variable DC voltage. Here input is the DC parameter as well as output is the DC parameter. That's why chopper circuits are called the DC to DC converters. And here chopper is represented by a power semiconductor device which is enclosed by a dotted square box. This is the representation of chopper. Any power semiconductor device which is enclosed by dotted square box, and this dotted square box represents the forced commutation. I think everyone know the concept of commutation. Commutation is nothing but the process of turning off the SCR. Here the input of the chopper is the DC variable, means DC value. Okay, in order to turn off the SCR, if the input is DC, we have to use some external circuit, and the process of turning off the SCR by using some external circuit is known as forced commutation. Okay, so this dotted square box represents the forced commutation, and here by using choppers we can step up or step down the DC voltage or DC power. In case of AC circuits, by using the transformers we can step up or step down the AC voltage or AC power. But in case of DC circuits, by using choppers we can step up or step down the DC voltage or DC power. That's why choppers are also known as the DC transformers. This bit is very important in gate point of view. Chopper circuits are also known as the DC transformers. Okay, this is the DC to DC converter or chopper, and the input for this converter is a fixed DC voltage or power, fixed power, and the output of this converter is the variable voltage or variable power. And this is the representation of fixed DC input, and this is the representation of variable DC input. This fixed DC input we are going to apply to this converter, and we are going to get this variable DC output as the output of this DC to DC converter. Okay, this is the representation of a chopper circuit. Here this is the power semiconductor device which is enclosed by a dotted square box. Okay, if we use the chopper circuit in low power applications, in place of power semiconductor device we have to use these power semiconductor devices. Those are GTO, IGBT, BJT and power MOSFETs are going to use it for the low power applications. Coming to high power applications, we are going to use the thyristors or SCRs in place of power semiconductor device. Okay, these two bits are very important in gate point of view. Okay, in the chopper circuit, in place of power semiconductor device, for low power applications, we are going to use these things, that is GTO, IGBT, BJT and MOSFET. Coming to high power applications, we are going to use the thyristors. Coming to applications of choppers, okay, DC to DC converters are applied for many applications, and these are the some of the major applications of DC to DC converters or choppers. In that, first one is the switched mode power supply systems, and second one is in DC motors as the speed controllers, and third one is the DC voltage boosters, fourth one is battery chargers, and next one is the railway systems, and finally electric cars. Okay, these are the some of the major applications of choppers. Coming to classification of choppers, based on the operating principle and type of the voltage source we are going to use, choppers are mainly classified into two types. Those are, first one is the DC chopper and second one is the AC link chopper. And based on the type of the commutation we are going to use, choppers are again classified into two types. In that, first one is the natural commutated chopper and forced commutated choppers. Okay, these two are based on the type of the commutation we are going to use. Again, forced commutated choppers classified into two types. Those are DC Jones chopper or Jones chopper, and second one is the Morgan's chopper. Depending upon the input and output voltage values, choppers are classified into three types. In that, first one is the step down or buck chopper, second one is the step up or boost chopper, and third one is the buck boost chopper. Okay, this is depending upon the relation between input and output voltages. And next classification is depending upon the power loss. Depending upon the power loss, choppers are classified into two types. In that, first one is the hard switching choppers and second one is the soft switching choppers. Okay, this is the entire classification of choppers. Now we are going to discuss about each and every type of chopper. In that, first one is the AC link chopper. AC link chopper, also known as the two-stage chopper. Why? Because in this chopper, while converting the fixed DC voltage to variable DC voltage, we are going to use the two stages. So it is called the two-stage chopper. And in this type of chopper, first DC voltage, first fixed DC voltage is going to convert it into the AC voltage by using the inverter circuit, and this AC voltage is going to step up or step down by using the transformer. Okay, after stepping up and step down the voltage, the output of this transformer is again going to apply to the rectifier circuit, and rectifier circuit is going to convert into the AC voltage to DC voltage. Here, by varying the firing angle of this rectifier, we are going to get the variable DC voltage, and this is the representation of the AC link chopper. Okay, in this DC input is going to apply to the inverter circuit. Here this one is the inverter circuit. Inverter is a circuit which converts the DC voltage to AC voltage, and the output of this inverter circuit is going to apply to the transformer. Okay, by using this transformer we are going to step up or step down the this AC output voltage. Okay, after stepping up or step down the voltage, the output of the transformer is going to apply to the rectifier circuit. Here rectifier is a circuit which converts the AC voltage to DC voltage, and this rectifier consisting of the thyristors. So by varying the firing angle of thyristor, we are going to get the variable DC voltage. Okay, this is the overall explanation of AC link chopper. It is called the two-stage chopper. Why? Because we are going to use the two stages while converting the fixed DC voltage to variable DC voltage. And this AC link chopper is the type of a chopper which is having the bulky in size and occupies the large amount of space. Coming to second type of the chopper, that is the DC chopper. Okay, this chopper also known as the single stage chopper. Why? Because by using single stage we are going to convert the fixed DC voltage to variable DC voltage, and this DC chopper works on the DC voltage, and depending upon the requirement we can step up or step down the voltage, DC voltage, by using this chopper. So this chopper also known as the DC transformer. Why? Because by using transformer we can step up or step down the AC voltage, but in case of DC, by using chopper we can step up or step down the DC voltage. So DC chopper also known as the DC transformer, and depending upon the requirement and depending upon the type of the chopper we can get the output voltage which is higher than the input as well as which is lower than the input value. And here DC choppers are more efficient. Why? Because we are going to use the single stage and we can get the output voltage, optimized output voltage within a fraction of seconds. Also, these DC choppers are the optimized devices. Okay, in this, these choppers provides the smooth control over the DC voltage, and this is the representation of DC chopper. We are going to use the single stage. By using this single stage, we are going to convert this fixed voltage to variable DC voltage. Okay, this is about the DC chopper. Now we are going to discuss about the step down chopper. That is, what is step down chopper, what is the power circuit, what is the analysis means working of step down chopper, related waveforms and characteristic parameters of this step down chopper. Here step down chopper also known as the buck chopper, and it is defined as the chopper in which the output voltage is less than the input voltage. That type of chopper is called the step down chopper, and this is the power circuit of step down chopper. The power circuit consisting of simply chopper circuit with anti-parallel diode and load, and here Vs is the constant fixed input voltage and V0 is the voltage across the load, and I0 is the current flowing through the load. Coming to analysis or working of step down chopper. The working of a step down chopper going to explain in two operating modes or two cases. Coming to first case, in this case we are going to consider chopper is in on state, and this is the equivalent circuit when chopper is in on state. Here this switch is closed. Okay, by closing this switch there is a path for current from source to load in the direction of Vs plus chopper, load and Vs minus. Here this diode is in reverse bias and this diode acts as a open circuit. So there is a path for current from source to load. Okay, and total input voltage is going to appear across the load. That is, when chopper is in turn on, Vs is directly appears across the load. That is given as V0 is equal to Vs. This is the first case of step down chopper. Coming to second case, in second case we are going to turn off the chopper. Means here chopper circuit act as a open switch. If chopper is act as a open switch means there is no path for current from source to load. If there is no path for current from source to load means the voltage across load is 0. That is V0 is nothing but 0. That is when chopper is in turn off, Vs is disconnected from the load. So output voltage across the load is 0. This is the second case of the step down chopper. Now by using this analysis, we are going to draw the waveforms. Okay, coming to waveforms, we know during on state of the chopper, we are going to get the output voltage V0 is equal to input voltage Vs. This is during the on state of the chopper. And during off state of the chopper, we are going to get the output voltage is equal to 0. Okay. Now by using these two values, we are going to draw the waveforms. Here this one is the input voltage waveform having the magnitude of Vs, and in first case we are going to consider the switch is on. When switch is on, we are going to get the output voltage is same as the input voltage. This is the waveform for output voltage. Here we are, when switch is on, we are going to get the this amount of voltage as the output voltage. Okay, this is the output voltage when switch is on. Similarly, if we consider switch is off, we are going to get the 0 voltage. This duration is the off state of the switch. In this case, we are going to get the 0 as the output voltage. If we consider load is the resistive load, then current follows the voltage but less in magnitude, and this is the waveform for current. The magnitude of this current value is Vs by R. So same as this load current follows the voltage but less in magnitude. During on state we are going to get this amount of current, and during off state we are going to get the zero current, and same cycle going to repeats. Means again during on state of the chopper we are going to get the Vs as the output. Again off state of the chopper we are going to get the 0. Here T on is the on time of the chopper. Similarly T off is the off time of the chopper. Vs is source voltage or input voltage. V0 is the output voltage or load voltage, and T is the chopping period. Okay, that is the summation of on time and off time. Okay, this is the chopping period, that is on time plus off time. Okay, these are the waveforms related to step down chopper. Now by using these waveforms we are going to derive the characteristic parameters. Coming to average output voltage of step down chopper. The general formula for finding the average output voltage is 1 by T into integral 0 to T f of t into dt. Okay, in step down chopper, output voltages exist in between 0 to T on. Okay, during off state of chopper, the output voltage is 0. So we are going to consider the limits are 0 to T on. Why? Because output voltages exist in on time of the chopper. So this formula is going to replace by this one, that is 1 by T into integral 0 to T on. Here f of t is nothing but function that is given as the output voltage. During on time of the chopper, output voltage is same as the input voltage. So f of t is considered as the Vs, that is integral 0 to t on Vs into dt. By applying the integration, here Vs is the constant, so take outside, that is Vs by t, and the integration for dt is t, and by substituting the limits 0 to t on we are going to get Vs into t on by t. Here t on by t is nothing but duty cycle, that is represented as the d. So the overall output voltage formula for step down chopper is d into Vs. Here d is the duty cycle, which is the ratio of on time to the total time. Here T on can be varied from 0 to T. Okay, by varying the T on from 0 to T, we are going to get the duty cycle range is from 0 to 1. Now by substituting the duty cycle value in between 0 to 1, we are going to get the output voltage which is in between 0 to Vs. Means output voltage is going to get the 0 to Vs, which is less than the input voltage. So we can conclude that output voltage is always less than the input voltage. So we can justify the step down chopper. Okay. Here output voltage is always less than the input voltage. So we can justify step down chopper conclusion. Okay. This is the formula for average output voltage. Similarly, we are going to derive the formula for RMS output voltage as well as effective input resistance. We know formula for finding the RMS value, that is given as square root of 1 by t into integral 0 to t f of t square into dt. Here also t is nothing but the time period and f of t is nothing but function. Okay, in between 0 to t and only output voltage exists. So we are going to consider limits as 0 to Tn. In place of f of t, we are going to consider the Vs square. Okay, by simplifying, we are going to get Vs into square root of Tn by t. Here Tn by t is nothing but duty cycle. So in place of this one, we are going to substitute the d. So RMS output voltage of step down chopper is square root of d into Vs. Similarly, the concept of effective input resistance. Here this is defined as the ratio of input voltage to the average output current. We know average output current in terms of voltage, that is input voltage by average output voltage by resistance. From that we can get Vs into R by average voltage. Okay, we know formula for average voltage. So in place of average voltage, substitute this formula. Then we are going to get the effective input resistance is R by D. Okay, these are the characteristic parameters of step down chopper. Average output voltage, that is V0 is equal to D into Vs. RMS output voltage, that is given as root D into Vs. Effective input resistance, that is given as R by D. This is about step down chopper or buck chopper. Coming to next one, that is the step up chopper. Here step up chopper also known as the boost chopper, and it is defined as the chopper in which the output voltage is greater than the input voltage is known as the boost chopper or step up chopper. And this is the power circuit of step up chopper. Power circuit mainly consisting of input source, inductor, chopper, diode and load. Okay, this is the power circuit of the step up chopper. Now we are going to discuss about the working of this step up chopper. How we are going to get the output voltage is greater than the input voltage. The analysis or working of step up chopper also going to explain in two operating modes. In the first operating mode, we are going to consider the chopper is in on state. In second operating mode, we are going to consider chopper is in off state. Okay, coming to first case, when chopper is in on state. Okay, and this is the equivalent circuit when chopper is in on state. Means this chopper circuit act as a short circuit. And here inductor going to charges, that is polarities plus and minus, and this negative polarity is going to connected to the anode of diode. So diode is in reverse bias, that is off state. Reverse bias which is in off state means this diode act as a open circuit. So there is no path for current from source to load, but there is a path for current in the direction of Vs plus inductor, chopper and Vs minus. So total input voltage going to appear across this inductor. Here when chopper is in on, it short circuits the load. Okay, here this chopper act as a short circuit, and hence total input voltage going to appear across the inductor, that is Vs is equal to VL. Here we know VL is nothing but L into di by dt, that is equal to Vs. From that we are going to find out the di. Here di is the peak to peak inductor current, that is given as Vs by L into T on. Here from this equation, in place of di we are going to write as the delta I. Similarly dt is nothing but this time. This is chopper is in on time, so dt is given as the T on. Okay, from that delta I by T on is equal to Vs by L. From that delta I is equal to Vs by L into T on. Consider this is equation number 1. Similarly, we are going to find out the delta I during when chopper is in off state. Coming to second case, when chopper is in off state. And this is the equivalent circuit of the second case. Here chopper is off means here this chopper circuit act as a open switch. And there is a path for current from source to load in the direction of Vs plus, inductor, diode, load and Vs minus. Here output voltage is the summation of supply voltage and inductor voltage. Here we will get the summation of both supply voltage as well as inductor voltage as the output voltage. That is given as V0 is equal to Vs plus VL. From that we are going to find out the inductor voltage. VL is equal to V0 minus Vs. Again inductor voltage, we know formula for inductor voltage, that is L into di by dt, that is given as V0 minus Vs. Again in place of di we are going to substitute the delta I, and in place of dt we are going to consider the off time. Why? Because this case is during the off state of chopper. So L into delta I by T off is equal to V0 minus Vs. From that we are going to consider the delta I, that is given as V0 minus Vs by L into Tf. Consider this is equation number 2. That is working of step up chopper during off state of the chopper. Now by equating above two equations, we are getting Vs by L into T on is equal to V0 minus Vs by L into T off. Okay. Here L gets cancelled. Then we are getting Vs into T on is equal to, that is Vs into T on is equal to V0 into T off minus Vs into T off. This equation. Now take this term to left side and take Vs as the common. Then we are getting this one. Vs into T on plus T off is equal to V0 into T off. Okay, from this equation we can write the expression for V0, that is given as V0 is equal to, here T on plus T off is nothing but total time T, that is T into Vs by T off. Okay, this expression we can write like this, that is Vs by T off by T, like this. Take this T2 down. So V0 is equal to Vs by T off by T. Here we can write T off as T minus T on, like this. That is Vs by T minus T on by T. By simplifying this expression, we are getting the average output voltage for a step up chopper. V0 is given as V0 is equal to Vs by 1 minus D. Okay, this is the expression for average output voltage of step up chopper. Now by varying the T on from 0 to T, we are getting the duty cycle range is from 0 to 1. Now substitute duty cycle value in this expression. Then we are getting the average output voltage, which is varies from Vs to infinity. So it is clear that the output voltage of the chopper is always greater than the input voltage. So it is called the step up chopper. Okay, this is about the step up chopper derivation of average output voltage. By using above analysis, we are going to draw the waveforms for step up chopper. We know two cases, that is during on time of the chopper, the output voltage is 0, and during off time of the chopper, output voltage is summation of the input voltage as well as inductor voltage. Now by using these two considerations, we are going to draw the waveforms. Okay, simple waveforms. Consider input voltage having the magnitude of Vs. Okay, this is the input voltage waveform. Input voltage waveform having the magnitude is Vs. Now coming to output waveform. During on state of chopper, we are going to get the output voltage is 0. Consider this is the on time of the chopper. During on time of the chopper, the output voltage value is 0. Okay, this is the output voltage during on time. Similarly, during off time, we are going to get the output voltage, which is summation of supply voltage plus inductor voltage. Okay, this is the off time. During this period, the magnitude of the output voltage is summation of supply voltage Vs plus inductor voltage VL. Okay, same cycle going to repeats for the remaining cycles. Okay, these are the waveforms of a step up chopper. Coming to next type of chopper, that is the Bugbush chopper or step up step down chopper. It is defined as the chopper in which the output voltage is less than or greater than the input voltage. That type of chopper is called the buck boost chopper. Now by using this buck boost chopper, we can increase or decrease the output voltage depending upon the requirement. Okay, coming to power circuit. Okay, this is the power circuit of buck boost chopper. It is consisting of chopper, inductor and diode. This diode is connected in anti-parallel direction to this chopper and load. This entire circuit going to supplied by the constant voltage source having the magnitude Vs. Okay, this is the power circuit of buck boost chopper. Now we are going to discuss about the working of buck boost chopper. Okay, in this also analysis going to explain in two operating modes. Okay, first operating mode is when chopper is in on state, and second operating mode is chopper is in off state. Okay, coming to first case, that is chopper is in on state. When chopper is in on state, that is act as a short circuit and diode act as a open circuit. Due to the open circuit of diode, there is no path for current from source to load. Total input voltage going to appear across the inductor. So inductor voltage is same as the supply voltage. Here VL is given as L into di by dt, that is equal to Vs. Here di is going to written as the delta I and dt is the on time. From that, delta I is equal to Vs by L into T on. Now for obtaining the duty cycle, we are going to multiply and divide by T. So delta I is equal to Vs by L into T by T into T on. So T on by T is nothing but duty cycle. So finally we can write delta I is equal to Vs by L, that is Vs by L, and T on by T is nothing but duty cycle D, and T, here T is 1 by T is nothing but frequency. So here T we can write as 1 by F. So finally we are getting delta I is equal to D into Vs by L into F. Consider this is the equation number 1. Okay, this is the change in current during on time of chopper. Similarly, we are going to find out the change in current during off time of the chopper. Coming to second case, that is when chopper is in off state. When chopper is in off state, inductor reverses its polarities and starts discharging through the load and diode. So we are going to get the output voltage V0 is equal to minus VL. Okay, again here VL is nothing but L into di by dt, that is given as the minus V0. From that we can write L into delta I by, here dt is nothing but off time. This case is during off time, so L into delta I by T off is equal to minus V0. Okay, here delta I is given as, from this find out the delta I value. Delta I is equal to minus V0 by L into T off. Consider this is equation number 2. Okay, this is the change in current when chopper is in off state. Now by equating the equation number 1 and equation number 2, we are going to find out the average output voltage of Bugbush Chopper. Now by equating equation number 1 and equation number 2, we are going to get this equation, that is D into Vs by F into L is equal to minus Vs by L into T off. Okay, from that L gets cancelled. Then we are going to get D into Vs is equal to minus V0 into T off into F. Okay, from that we are going to find out the V0 value. Okay, by simplifying this one, we are going to get V0 is equal to minus D into Vs by 1 minus D. Okay, by taking only magnitude, we are going to get the V0 is equal to D into Vs by 1 minus D. Here D is the T on by T. Okay, from that we can write T minus T off by T. Here T on is the T minus T off. Okay, from that we are going to get the 1 minus D. This is the average output value of a buck boost chopper. Now when D is equal to 0, we are going to get the output voltage is 0 and D is equal to 0.5 in this equation. Then we are going to get the output voltage is equal to input voltage. Similarly, substitute D is equal to 1 in this equation. Then we are getting the V0 is equal to infinity. Okay, from these observations, it is clear that for the interval 0 to 0.5, for the interval 0 to 0.5, the output voltage is varies from 0 to Vs, and we can get the step down chopper or buck operation. Similarly, if the duty cycle range is from 0.5 to 1, then we are going to get the output voltage is from Vs to infinity. So we are going to get the step up operation or boost operation. So by using this conclusion, we can conclude that Bugbush Chopper. This is entire thing about the Bugbush Chopper. Up to now we discussed about the different types of choppers. Now we are going to concentrate on the classification of chopper circuits. Okay, depending upon the directions of output voltage and output current, these chopper circuits are mainly classified into five types. Those are from type A chopper to type E chopper. Here direction of voltage and current is nothing but quadrant operation. That is depending upon the current and voltage values. Current and voltage values, we are going to get the quadrant operation. If the voltage and current both are positive means we are going to get the first quadrant operation. If voltage is positive and current is negative means we are going to get the second quadrant operation. And if voltage as well as current are negative means that is the third quadrant operation. Similarly, if current is positive and voltage is negative means fourth quadrant operation. Depending upon the quadrant operations, this classification is made. That is from class A chopper to class C chopper. Now I want to give the introduction to these chopper circuits. From class A to class E, some choppers going to operate only in single quadrant. Those type of choppers are called the single quadrant choppers, and some choppers going to operate in two quadrants. Those type of choppers are called the two quadrant choppers, as well as some choppers going to operate all in four quadrants. So those type of choppers are called the four quadrant choppers. Coming to Class A chopper works in the first quadrant. That is nothing but in this chopper we are going to get the both output voltage as well as output current are the positive values. And in this type A chopper, power always flows from source to load, and the output voltage is always less than the input voltage value. So type A chopper is similar to the step down chopper. Okay, type A chopper is the example for first quadrant chopper. Coming to type B chopper works in the second quadrant chopper. In second quadrant, voltage is positive but current is the negative. Okay, current is the negative. So power is flows from load to source. This is the second quadrant. Okay, in this voltage value is positive and current value is negative. So type B chopper works in the second quadrant. Here load voltage is positive but load current is the negative. So power flows from load to source, not a source to load. Load to source. And this type of chopper is the example for step up chopper. So type B chopper is the second quadrant chopper, and it is a one type of step up chopper. These bits are very important in gate point of view. Similarly, if we consider class C chopper, okay, class C chopper is going to formed by connecting the class A, that is type A and type B choppers in parallel. Okay, by connecting type A and type B choppers in parallel, we are going to get the type C chopper. And coming to type D chopper is a two quadrant type B chopper. Here type C chopper is a two quadrant type A chopper, and type D chopper is a two quadrant type B chopper. And coming to type E chopper, by using type E chopper, we are going to get the four quadrant operation. So type E chopper is the example for four quadrant chopper. These bits are very important in gate point of view. Type A chopper is the first quadrant chopper. Voltage and current both are positive. Type B chopper is the second quadrant chopper. Type C chopper is the two quadrant chopper, and type D chopper is also a two quadrant type B chopper, and type E chopper is the four quadrant chopper. Coming to circuit diagram and quadrant operation of different types of chopper circuits. Okay, first one is the type A chopper. Type A chopper is the example for first quadrant chopper. Okay, this is the circuit diagram of type A chopper. Okay, it is consisting of chopper, anti-parallel diode load. Here load is consisting of combination of R, L and voltage source of magnitude E. This entire thing is going to supplied by a constant voltage source Vs. Okay, in type A chopper, we are going to get voltage as well as current. Both are positive. Okay, this is the quadrant representation of a type A chopper. Here, type A chopper is the first quadrant chopper. Okay, in this voltage as well as current both are positive. And in this operating mode, type A chopper act as a forward motoring mode. Okay, this bit is very important in gate point of view. Type A chopper operates in the forward motoring mode. Okay, this is about type A chopper circuit diagram and quadrant representation and operating mode. Similarly, we are going to discuss about remaining types of chopper circuits. Coming to type B chopper also a single quadrant chopper, but it is operated in a second quadrant operation. It is operated in second quadrant. In second quadrant, voltage is positive, but current is a negative. So, in this chopper circuit, power is flows from load to source. And this is the circuit diagram of type B chopper. Okay, it is also consisting of diode and chopper load. Load is the combination of R, L and E, and this entire thing going to supplied by a constant voltage source Vs. Okay, and this is the quadrant operation of a type B chopper. Okay, here type B chopper operates in the second quadrant and it operates in a forward braking mode. This bit is very important. Okay, type B chopper operates in a forward braking mode. Type A chopper operates in a forward motoring mode. This is operates in a forward braking mode. Coming to type C chopper or class C chopper. Okay, by using type C chopper, we are going to get the two quadrant operation. That is first quadrant as well as second quadrant operation. Okay, in type C chopper, voltage is always positive, but current is positive as well as negative. Okay, so power can flow from source to load as well as load to source. And this is the circuit diagram of class C chopper. By connecting the class A as well as class B choppers in parallel, we are going to get the type C chopper. And this is the quadrant operations of type C chopper. This is the first quadrant in which voltage and current are positive, and we are going to transfer the power from source to load. And this is the second quadrant operation. In this voltage is positive but current is negative. So power is flows from load to source. Okay, this is about the type C chopper. Similarly, by using class D chopper, we are going to get the two quadrant operation. That is first quadrant as well as fourth quadrant operation. And by using the class C chopper, we are going to get the four quadrant operation. Means all four quadrants we are going to operate by using class C chopper. Okay.